First 5G network deployments are based on non-standalone mode, using an LTE carrier as an anchor for the exchange of signaling and control information. 5G is now added utilizing dual connectivity functionality. These 5G connections are today either taking advantage of FR2 millimeter wave frequencies, or for lower frequencies, FR1 frequencies, these are right now only TDD bands. As an example, all network deployments below 8 GHz are using either the N77 or N78 band, in other words 3.5 GHz, which is only a TDD band. There's no FDD-based 5G network deployments as of the second half of 2019, even if the majority of cellular bands below 7.125 GHz are organized as FDD bands. This is due to the industry still working on the support for FDD for 5G NR. However, these frequencies are already heavily utilized by today's LTE advanced networks, applying features like carrier aggregation to boost the data rates and increase overall system capacity. Due to the spectrum already being in use by LTE, network operators worldwide are facing a dilemma if they would like to deploy a coverage layer for 5G using lower frequency bands. So the question is what to do. Acquiring new spectrum is an alternative, but in most countries not applicable as there is none available. Refarming means opening up LTE frequencies and use them for 5G NR is an option, but this is typically very costly as hardware and software changes are required. The alternative is what the 3GPP standard summarizes under the umbrella NR-LTE coexistence as dynamic spectrum sharing, short DSS. So let's take a look at how this feature is supposed to work. Dynamic spectrum sharing, what is it? So let's take a look at what we have deployed today. I oversimplify the situation in networks, of course, if you're looking at that. Taking an example here with two frequency bands, X and Y, where LTE carriers are deployed, for instance, utilizing different bandwidths. In the example here, 20 megahertz and 5 megahertz. So they're combined over the feature called carrier aggregation. Of course, state of the art today for the operators is the aggregation of 4, 5 carriers in downlink, 3 carriers in uplink as an example. But in order to understand the feature, we of course don't need to do that here with 5 carriers, just sticking to 2. So dynamic spectrum sharing now means the following, that by 2020, the standard has defined 2 different modes. So the one is using this feature in the terms of frequency division multiplex, the other one in time division multiplex. So frequency division multiplex, as you can see here, what we simply do, or the idea is splitting up the spectrum, in the example here with my 20 megahertz carrier, for instance in 2 times 10 megahertz, where one component or part of that spectrum, 10 megahertz, is still being utilized for LTE, and the other part is then now a newly deployed 5G NR carrier. So this is the FDM approach. The TDM approach, of course, means now that we utilizing the spectrum, but sharing it from a time division perspective. And what I'm showing here is basically now the focus from a downlink perspective. That means we're looking from the downlink side, and the idea is now basically to punch out certain subframes while utilizing the feature called MBSFN, so a multimedia broadcast single frequency networks subframes, which means we empty the LTE subframe, and those empty LTE subframes could now be utilized by 5G NR. So this is the fundamental idea. So basically we're talking about either an adjacent channel approach when we do FDM mode for dynamic spectrum sharing, or a co-channel approach when we are doing TDM approach. So, but that is not everything, of course. There's many more fundamental features required to enable dynamic spectrum sharing. The first one I already explained with MBSFN subframe support. But then, of course, you see here that we need to have certain mapping functionality for the data channel in 5G NR. Certain aspects for the monitoring of the control channel need to be supported. Something that is called alternative additional DMRS position, some rate matching capabilities, and also to enable that on the uplink side, an alignment of the channel raster to avoid interference. Of course, we need to take a look at all these features to understand how DSS is working within the 5G NR standard. And from that perspective, let's take a closer look to the individual feature sets enabling DSS. So first of all, the MBSF subframe configuration, it's an LTE feature that needs to be applied to the LTE carrier, defined to enable broadcast over the LTE standard. The relevant information is broadcasted by the LTE network in System Information Block Type 2, where we have an information element called MBSFN subframe configuration. And that information element basically gives me now the allocation or configuration which subframes within the radio frame can be used for broadcast. That was the initial idea. So you see here on my screen basically a full radio frame with 10 subframes, so 10 milliseconds long. Not each and every subframe within the LTE radio frame can be configured to be a broadcast subframe. So for instance, the subframe number 0, number 4, number 5, and number 9 can never be utilized as broadcast. Simple reason is in some of them are synchronization signals being transmitted, primary and secondary synchronization signal, and the others are being utilized for paging. So that leaves us with 6 out of 10 subframes, and now this MBSFN subframe configuration element will exactly tell me the periodicity, the allocation, and in my example you have here the purple ones being configured, and that is of course being signaled to the device as broadcast function in the SIP type 2, as I explained earlier. So now is the question, why are these MBSFN subframes required? Well, we need to enable the 5G NR device to basically synchronize towards the signal, and for that we need to transmit the so-called synchronization signal blocks. So we empty out the LTE subframe. Here in my example, you can see that here highlighted in blue. It's basically the second subframe within an LTE radio frame that is being configured. Of course, by default, we don't want to take away resources from the LTE side significantly, so it's 1 out of 10. So 10% in this example, and it's emptied out. It's becoming an MBSFN subframe, but of course an MBSFN subframe by definition, as it is standardized in LTE release 9, is not completely empty. In fact, it has a so-called non-MBSFN region, which is the beginning of each subframe that could be either 1 or 2 symbols long, so seen here, and this is needed to still transmit the LTE control channel, the PDCCH, the PHIH and the PCFIH, so significant channels embedded into the overall LTE physical layer structure. And on those 2 symbols, of course, I'm still having the LTE cell-specific reference signals being present. So what you basically see there now, out of the 14 symbols within that subframe, 2 are still occupied by LTE content. So that leaves me with 12 symbols left that I can now transmit in the 5G NR core set, the data channel, and then of course the demodulation reference signals for the data channel. So now looking at that, you see here basically 2 symbols being occupied with the DMRS. That has basically coming with the definition of DMRS in 5G NR, which you can specifically see here, coming out of 38.2.11, the physical layer and modulation specification. And am I having those number of symbols left, then you see basically that my additional DMRS is being transmitted in symbol number 9 out of that subframe. So this is one aspect of DSS, enabling a 5G NR device to sync to the 5G NR signal. Therefore, we need MBSFN subframes. But what are now about transmitting 5G NR in other subframes that are not configured as broadcast channels? So as indicated here, I already mentioned a few of them are needed for synchronization signals, PSS and SSS, and also paging. But what about the other ones that are not configured as MBSFN? Can we use them? And the answer is twofold. Yes, we could, but still the LTE physical layer design gives us a challenge here, and we need to work around this designed to enable the use of those particular subframes. So to come to this challenges that we have as the PDSCH, even if it is not transmitted there, the LTE PDSCH, I mean, they are not completely empty. So there are still cell-specific reference signals being present and such, and that is the mentioned challenge that we have to work around. So let's take a first look at how we overcome this. You see here a basic snapshot of how configurable the NR physical layer is in terms of mapping, in particular of the data channel and the demodulation reference signals. So as you can see here, based on higher layer configuration that I put out here, you can define things like the density, the additional positions for these demodulation reference signals, where it's actually starting is broadcasted in a master information block. So a lot of information to flexibly configure these signals. However, it always depends on what's being signaled. And if we're looking at now the idea that we're using a full subframe with 14 OFDM symbols that are LTE subframes, so no broadcast, but we still transmit NR PDSCH in it, then we have certain mapping principles that we see here for these mapping types, which is usually means that an additional position for these demodulation reference signals is the symbol number 11. So if we now take a closer look at a subframe, in my example here I'm using the third one, that is still LTE, but I want to transmit NR in it, then I can clearly see I have a number of challenges. I have the LTE cell-specific reference signals still being present. And that is my particular challenge because, as I showed you earlier, symbol number 11 is the one that should help with the, or should carry the demodulation reference signals. But as you can see clearly here, there is still the LTE cell-specific reference signals present. So the standard defines in that particular case an additional DMRS position, as I indicated earlier. So that means basically we move this transmission from symbol number 11 to the 12th symbol in the subframe, as indicated here by the graphic. And if we're looking at that, that's support of additional DMRS position is a UE capability. That means a DSS capable device will indicate that towards the network as a UE capability parameter, which is only specified for frequency range 1. And as you can see here down, only for the case for 15 kilohertz of subcarrier spacing. So as you can see, a number of parameters needs to be signaled in addition. For instance, the rate matching, which we come to in a moment. A certain position for the first DMRS should be set, in this case starting in symbol number 3. And then, as you can see here, the indication of this feature set is necessary in order to do that. So there's a number of information also being exchanged between the network if the UE is capable of doing this DSS, and these are the parameters that are necessary. So last not least, I talked about the rate matching. You have seen in the graph that the LTE cell-specific reference signals are still being present. So I need to have a rate matching feature enabled. Basically, NR doesn't transmit any types of data on resource elements that are carrying LTE-specific reference signals to avoid the interference. So best explained here by using that functionality that's already implemented into a Rohde-Schwarz vector signal generator, the SMA200A. So as you can see here, this is activated. We have 4 information elements that need to be configured. First of all, to align the channel raster, the frequency settings for 5G and R needs to be applied here. Basically, the offset from point A over 15 kilohertz subcarrier spacing. So that's item number 1. The second one is that we have a certain shift to be applied, which is dependent on the physical cell ID that's being used. That's a modulo 6 operation that you can see here, because that's why they are cell-specific reference signals, as their position is based on the PCI. And then, of course, you need to configure bandwidth parameters, like what bandwidth is used. In this case, it's 5 megahertz of bandwidth with 25 resource blocks. And then, of course, last not least, what type of MIMO is applied. In this case here, it's 2x2 MIMO. As you can see, as 2 LTE antenna ports are used. But there's also the possibility to do that for 4, of course. It's just a example. So all this information that you see here on this particular slide is actually being signaled to the device over the established LTE connection so that the LTE rate matching is active. Another set of information is now, we talked a lot about the downlink functionality. What about uplink? So uplink sharing from a UE point of view is also a UE functionality, as you can see here, that the device is indicating towards the network if it now supports the TDM functionality, FDM only, or even both. And then again, this is for frequency range 1 only, so it's something in addition that the device signals to the network so the network knows what's going on. So with that, we have all the parameters discussed on the physical layer aspects, how it's being delivered to the device. Now you can imagine we're using dual connectivity, LTEs and NR, both independent networks with 2 schedulers. So how is that going to work together? Well, of course, there are also RAN and core network aspects for DSS. So if we take a look to that, you basically will see that between the G node B, so the 5G RAN, and the E node B, the LTE RAN, we have the link established over the X2 interface. So what you basically see here is the 2 methodologies that can be initiated from the LTE side or the G node B side. So here's initiated from LTE, this is from 5G. So basically what is being done is there's an EUTRA NR cell resource coordination happening. You see here spectrum sharing group IDs being utilized, how many cells participate in this coordination between an NR, an LTE cell and vice versa. And the most important piece is now how the data traffic transmission is being coordinated, and that's an information element that you can see here. We basically define on which system frame number, so which radio frame this is being applicable. And then you have 2 bitmaps, downlink, as well as, uplink as well as downlink. And this information, as you can see here, is now a bitmap with a certain length. And it will determine which of these radio frames is then being utilized for downlink, uplink, push, PDSCH, and so forth. And that's the information that's being exchanged between the 2 network sites, between the 2 RANs, the 5G RAN and the LTE RAN. So this is in brief basically what is necessary to enable dynamic spectrum sharing. After this overview of the technology, I would like to demonstrate this functionality to you using Rohde & Schwarz test and measurement equipment. But this is another topic for another video in our video series, Demystifying 5G.